In this illustration, we intend to simulate the entry of the pendulum into the water using coupled Eulerian-Lagrangian method in Abaqus software. Actually, the pendulum has a reciprocating movement which causes the pendulum to enter the water, and the water becomes turbulent. In this problem, the initial angle of the pendulum with the vertical axis is 60 degrees. Then the pendulum undergoes the weight of its own load, and that causes the pendulum to have an oscillating motion. Over time, the amplitude of the pendulum oscillating motion decreases until it comes to absolute halt. You can observe the motion of pendulum and turbulence of water in this animation. I will click on Create Part. Here I intend create geometric shape of Eulerian part. Here I will select the modeling space as 3-dimensional, then select Eulerian, enter approximate size equal to 0.5 and continue. I will draw a rectangle, enter its length equal to 0.25 meters and its width equal to 0.125 meters. Done. Enter its depth equal to 0.125 meters as well, and OK. I will click on Tools menu, select Datum. From here select Plane and then Offset from Plane. Select this plane, enter value, flip and OK. I will enter offset equal to 0.05 meters. In the next step, I will click on Tools menu, select Partition. From here, select Cell, and then use Datum Plane. Select this Datum Plane, and then click on Create Partition. I will click on Create Part. Here, I intend to create geometric shape of pendulum. Here, I will select Deformable, Solid, and Revolution. Continue. I will draw a semicircle and enter its radius equal to 0.01 meters. In the next step, I'll draw a line like this. Enter its length equal to 0.1 meters. I will enter the distance between this point and the symmetry axis equal to 0.02 meters. In the next step, I'll click on Auto Trim and delete this line. In the next step, I will complete the shape. Done. Enter the angle of rotation equal to 360 degrees. In the next step, we should create partition over the pendulum. I will click on Tools menu, select Datum. Here select 3 points and then select these 3 points. I will click on Tools menu, select Partition. Here select Use Datum Plane. Select this datum plane and click on Create Partition. After that, I'll select these 3 points. And then create partition over the model using this datum plane. I will enter Property module. Click on Create Material. Here, I intend to define the properties of water. I will click on General menu, then on Density. The density of water is equal to 1000 kilograms per cubic meter. In the next step, I will click on Mechanical menu, select EOS, and here EOS is the same equation of state. Then here I'll select USUP. The sound speed inside the water is equal to 1500 meters per second. In the next step, I'll click on Mechanical menu, Viscosity. The dynamic viscosity of water is equal to 0.001 Pascal seconds. OK. I will click on Create Section. Here select Solid and then Eulerian. Continue. Then I'll select Water, Material and OK. I will click on Assign Section. As you observe, Eulerian part was automatically selected. OK. Again, I will click on Create Material. I intend to define the properties of steel. I'll click on General menu, then on Density. The density of steel is equal to 7,800 kilograms per cubic meter. Select Elasticity and Elastic. The Young modulus is equal to 200 multiplied by 10 to the power of 9 Pascal, and the Poisson ratio is equal to 0.3. OK. I will click on Create Section. Here select Solid and Homogeneous. Continue. Select Steel Material. OK. I'll click on Assign Section, select Pendulum, Done, and OK. I will enter Assembly module. Enter both parts of Eulerian and Pendulum into the Assembly section, and OK. I'll click on Translate Instance, select Pendulum, Done. First, select this point, then this one, and OK. I'll click on Translate Instance, select Pendulum, Done. First, select this point, then this one, and OK. Again, I'll click on Translate Instance, select Pendulum, Done, and move Pendulum as much as 0.015 meters downwards. Again, I'll click on Translate Instance, select the whole of the model, Done. First, select this point, then select Coordinates System, and OK. In the next step, I click on Rotate Instance. Select Pendulum. Done, and rotate pendulum as much as 60 degrees about Z-axis. In the next step, I click on Tools menu, select Reference Point, select this point. Click on Tools menu, select Reference Point, select this point. After that, I'll enter Step module. Click on Create Step. Here, select Dynamic Explicit. Continue. I will enter time period equal to 1.5 seconds and OK. I'll click on Field Output Manager. Edit. Here, I'll enter the number of frames or the same outputs equal to 150 and OK. I will enter Interaction module. Click on Create Interaction Property. Select Contact. Continue. And OK. Then I'll click on Create Interaction. Here select Contact. Continue. OK. After that, I'll click on Create Constraint. Here select Rigid Body. Continue. Here we intend to convert the deformable pendulum into rigid pendulum. Here I'll click on this arrow, select Pendulum. Done. Then click on this arrow and select this reference point. I will click on Create Constraint. Here select Coupling, Continue. Select this reference point. Done. Click on Surface and select these surfaces. Done and OK. In the next step, I'll enter Load module. Here click on Create Boundary Condition. Select Displacement Rotation and continue. I will select this reference point. Done. Here I'll close all boundary conditions of displacement except UR3. In this manner, our rotation about Z-axis would become free. In the next step, I'll click on Create Boundary Condition. Select Velocity, Angular Velocity. Continue. Select these surfaces. Done. And here select V1 and OK. Once again, I click on Create Boundary Condition. Select Velocity, Angular Velocity. Continue. Select these surfaces. Done. Select V3 and OK. Once again, I'll click on Create Boundary Condition. Continue. Select the bottom of the model. Done. Close the boundary condition of V2 for it and OK. Then I'll click on Create Load. Here select Step 1. Then select Gravity. Continue. I will enter acceleration of Earth gravity equal to 9.81 meters per squared second. OK. In the next step, I'll click on Create Predefined Field. Select Initial Step. Then select Material Assignment and continue. I'll select Eulerian part. Here, right-click and select Edit Region option. Here, I should select the area on which there is water. Here, I will select this part. Done. Actually, the part having been marked out with pink color is the area on which there is water. In fact, the bottom part of Eulerian is composed of water, but the top part is void. In the next step, I'll enter Mesh module. Done. Here, first I select Hex Dominated option, then Sweep. Here, I'll select Medial Axis and OK. Then I'll click on Seed Parts, enter approximate global size equal to 0.0025 meters. OK, then click on Mesh Part and Yes. I will click on Assign Element Type, select a pendulum, done. Here select Explicit and OK. Here I'll click on Seed Parts, enter approximate global size equal to 0.0025 meters. OK. Click on Mesh Parts and Yes. Here I will save the model. I will click on Create Job. As you observe here, the amplitude of pendulum motion will gradually decrease, or in other words, the velocity of pendulum motion will slow until it comes to an absolute halt. This issue can be observed quite well in this animation. Here, you observe the initial state of the pendulum, and you see that the pendulum comes to an absolute halt after it has been oscillated for several times. Now we want to draw this diagram, the diagram of pendulum motion. I will click on Create XY Data, select ODB, Field Output, and continue. Here, I'll select Unique Nodal, then displacement directed at X. Select this point and click on Save. Here you observe the diagram of the pendulum motion. As it's clear in the diagram, the amplitude of pendulum oscillation gradually decreases until the pendulum stops completely.